Good morning, dear student. So let's start our class. So my dear student, today we will start our new chapter. That is chapter number 12, and in this chapter we will learn about thermodynamics. Okay. So my dear student, thermodynamics is that branch of the physics which deals with heat, temperature, okay, and conversion of mechanical work into heat, and also heat are converted into mechanical work. So these all things are studied in the branch of physics that are thermodynamics. Okay, and now first topic of our this thermodynamics chapter is thermal equilibrium. Here, thermal equilibrium means it is a condition when the system, okay, two or more system that are contact to each other will have a equal temperature. Suppose if I take this a closed system and again I contact the another closed system, then what we will see, if this system have a 10 degree Celsius, suppose, okay, and in the initial state it has a 10 degree Celsius and it have a 5 degree Celsius, but when it will contact to each other and we observe after some time these two system have a equal temperature, like it will become a 7 degree and also this system also having 7 degree Celsius. Then you see here this equality, that condition is our thermal equilibrium. Now it means when they have the greater in initial state they have the greater temperature and another have a lower temperature, but after some time we see that both are equal. That means they sharing some temperature. Okay, that means the temperature is that physical quantity which are equal, the condition, okay, or to make the thermal equilibrium. So from that we form a new law. That law is the zeroth law of thermodynamics. In that law we do we some take some situation. Here we take a three system, okay, and every system are contact but two system are separate to each other. Okay, now suppose you see this is the third system, A, B, C. A is first system, B is second system, and C. And you can see also in this picture we contact the system A and third system, that is system C. Okay, and also we contact B and C and we separate the A and B. Then we see that when we contact two system, then what will happen? Thermal equilibrium condition is achieved, right? That means C, the temperature on C and temperature of A will equal. Okay, similarly we observe in that contact point where B and C are contact. Here also we get B and C are equal, their temperature will equal. Then we conclude from that the temperature of A and temperature of B also equal. Okay, that is our zeroth law. If two bodies A and B are in thermally equilibrium with third body or third system, then A and B are also in thermal equilibrium to each other. Okay, and you just suppose if A is at 10 degrees Celsius, okay, and C is also 10 degrees Celsius, that means both are equal, that means both are thermally equilibrium. Okay, and C is 10 degrees Celsius, that means B also have a 10 degrees Celsius, then we called as a B and C are thermal equilibrium. Okay, then when we observe system A and system B, you see A also 10 degrees Celsius and B also have a 10 degrees Celsius. That means A and B are in thermal equilibrium. Okay, that is the zeroth law. And from the zeroth law, we just simply make a concept. System A is thermal equilibrium with C. That means the temperature of A and temperature of temperature of C are equal. And similarly, if temperature of B and temperature of C are equal, then when we observe that, we get temperature A and temperature B is equal. Okay, that is the concept of our zeroth law. And from this, we take a new physical quantity, that is temperature. And temperature is that physical quantity which are make the system, two different system make a thermal equilibrium. Okay, now next is heat, internal energy and work. So first of all, we discuss about heat, and it represented by Q. Okay, here heat or amount of heat, okay, that's are represented by capital Q. And heat is the mode of energy which transfer, okay, and that transfer from one system to another due to the difference of temperature. Okay, when system will achieve thermal equilibrium, that means there is no transfer of energy. Okay, but when there have some differences, in that case 10 degrees Celsius initially and that's a 5 degree Celsius, they have the some differences na. In that case the energy are transfer, okay, due to this temperature difference. And then it means heat are transferring, matlab heat are flowing, right? When here you see I take this two system na. Now here I take this, if I take this one system, this is the system, a closed system, right? And outside of this system, that is our surrounding. Okay, when heat or flow from surrounding to system, okay, that means heat are flowing from surrounding to system, then we put positive sign for heat. Okay, that means heat flow have a positive sign when heat flow from surrounding to system. And just opposite, their opposite, when heat flow from system to surrounding, then we represent it with negative sign. Okay, here in first case when we put positive sign, it means system gain the heat, right? System are gain heat, right? And in second case system lose their heat, that means heat loss. Okay, when we put negative sign, that means heat loss, and when put positive sign, that indicate heat are gain. Then after that, internal energy is the total sum of the kinetic energy of all particles and sum of the potential energy of all particles. Okay, and this internal energy is represented by capital U. Okay, and if in calculation we get positive sign for U, that means internal energy are increased. Okay, and negative sign indicates that internal energy are decreasing. Now next one is work, the energy that is transferred from one system to another by the applying force. Okay, then that energy move along with the direction of force, that is our work. And that work are expressed for closed system. Okay, you see this is a closed system, here this is the piston. Okay, and here some gases are present, That means this gas have some pressure, okay, and this system have some volume na, and here some temperatures are there. Now when we give some heat, okay, by give heat, okay, that means Q, then what will happen, that gas present inside the system get this heat, and gas in the cylinder is in thermal equilibrium with surrounding at a temperature T. Now when these gases have a pressure that is represented by F by A, and F is equal to PA, and now this, when these gases absorb heat, then what will happen, their gas are expand their volume, okay. That means that gases are doing some work, okay. That's why you called work done by the gas, okay, because that gas expand their volume. In that case we observe that the volume will increase. That means piston go upside, okay, and this volume will gradually increasing, okay. Now we written this work done by the gas, that is the small work done, that, and work done is F into dx means distance, okay, and F is equal to PA, then PA dx, and we know area into this dx distance is become volumes, then dW is P dV, okay. Now if volume of gas is increase, okay, from initial V1 to V final volume, then we get this relation, okay. Now after solving we get this one, okay. Then this relation represent work done, this work done by the gas, okay, and due to work done by gas we observe that this volume will increase, okay. And if volume is decreased in that system, in second system you observe when piston is moving downside, that means what happened, their volume will decrease, right. Then in that case we say that piston, okay, move due to the some external force, right. And when this happen, then we say that work done, this piston are working, okay, in the system, then we call work done on the system or on the gas, okay. When gas are expanding, then volume will increase. In that case we call work done by the gas, and when some external force are applied, due to that volume will decrease, then we call as work done on the gas, okay. Now we get this relation when W are positive, okay, positive sign, that means work done are by the system, okay, work done by the system or gas. And if we get W have a negative sign, that indicate work done is done by the work done here work is done on the system or on the gas, okay. Then after that, first law of thermodynamics. Here first law of thermodynamics means when we give some energy, assume energy, that means heat, okay, in the system, then that heat are distribute or utilize, okay, by the particles to increase their kinetic energy. And when kinetic energy will increase, that means their internal energy will be changed, okay. And due to that the system doing some work, okay. That means how much we give the energy or heat, that much of energy are distributed to increase their internal energy and doing the some work, okay. That means if we put 110 joule, then it means this 10 joules are distributed to increase internal energy. Suppose 5 joule are used to increase the internal energy and remaining 5 joules are used or utilized by for doing some work. Okay, so you see this total 10 joule are distributed in increasing energy, internal energy and doing some work. Okay, that is our first law. Here, if a system absorbs heat such that internal energy is changed and system does work, okay, and their relation we get, that is Q equal to change in internal energy plus work done, and we know work done is also expressed in terms of pressure and change in volume. Okay, so that is our first law of thermodynamics, and from first law of thermodynamics we can define internal energy. Okay, here you see internal energy is difference of the heat, absorbed heat and work done. Okay, so you can see the difference between internal energy is also defined as the difference between heat energy and work done. Then after that, specific heat capacity. Specific heat capacity means the amount of heat, okay, the amount of heat required to rise the temperature of unit mass through unit degree. Suppose we take 1 kg of water, okay, and that water initially have a 10 degrees Celsius. Okay, now if we want to increase their temperature from 10 to 11 degrees Celsius, okay, so you see only we want to increase 1 degree, only 1 degree. That means we need some energy to rise their temperature, right? And their mass is unit. Okay, the same unit 1 kg of water when increase their temperature from 10 to 11. Okay, now they require some heat. Now that amount of heat is our what? Specific heat capacity. Okay, that is represented by small c. That means specific heat capacity is the amount of heat which are required to rise the temperature of unit mass through unit degree. Okay, their mass is equal but their temperature are from 10 to 11. Okay, now again 11 to 12, then their temperature again they needs the some heat. Okay, now that heat is our what? Specific heat capacity. Now heat capacity are two types. Okay, that is heat capacity at constant volume, it is represented by Cv, and heat capacity at constant pressure, that is Cp. Okay, and when we put constant pressure, in that case the heat capacity is greater. Okay, for example, we take this same case. Okay, this same thing. If we take 1 kg of water and their initial temperature is 10 degrees Celsius and we want to increase their temperature from 10 to 11, and here we put pressure at a constant. Okay, we kept pressure constant, then what will happen? The amount of heat, suppose to increase their temperature we get 10 joules. Okay, but when we put constant volume and again we rise their temperature, then we see that only 8 joules are need to rise their temperature. Okay, then we get some differences. When we put pressure at constant, at the time the amount of energy is 10 joule, but when we kept volume as constant, then we see that the amount of energy is only 8 joule. That means at constant volume the amount of energy is less than the specific heat at a constant pressure. Okay, so it means why this is happen. Now when gas is heated at constant volume, okay, when we put volume at as a constant, then when we heat, that means we giving some energy, then that energy or all heat is used in increase their temperature of gas. Okay, that means how much we give the heat, that heat are used only increase their temperature, and no heat is used in expansion of gas. Okay, because all the heat are utilized to increase their temperature. Okay, that means all heat are only increase the temperature, and no heat is used in expansion of gas. Okay, but when we put pressure as constant, in that case some part of the heat are used to increase the temperature. Okay, and some part of the heat is doing some work to increase the volume of the gas. Okay, that's why at a constant pressure have a high value of specific heat, okay, as compared to specific heat at a constant volume. So it represent it, we conclude from this thing some additional amount of heat is equal to work done. Okay, so that is why Cp is that greater than Cv. And you see here specific heat is the amount of energy need to rise temperature of 1 kg of a material by 1 degree Celsius, and this is the relation for the specific heat. Okay, you see this is the specific heat is equal to Q is the heat, okay, or energy, amount of heat or energy by mass of the gas and change in the temperature. This equation is, this relation is also written as like this. Here E is the, Q is just same. Okay, here E written and here Q, and this is equal to M into C, and this M is the mass, C is the specific heat capacity, and theta is the change in temperature. Okay, and here also give their unit also, you remember their relations. Okay, their unit. Okay, especially here unit of the specific heat. Now after that specific heat now now we had learned specific heat at constant volume is represented by Cv, and specific heat at constant pressure is Cp, and we know Cp is greater than Cv. Okay, now question is arise, this Cp, how much Cp, how much amount of Cp is greater. Okay, what is the difference between here, and how we know what is the difference. Okay, so we take the ideal gas. Okay, so we consider a mu moles of ideal gas at pressure P and T. So according to first law, we know amount of heat is equal to amount of change in internal energy plus work done. Okay, now at constant volume, dq means heat rise to temperature. Okay, dt, but there is no change in volume. Okay, because we put constant as volume, constant is volume as a constant. Okay, that means dv is 0, then we get this relation, this one, dq is just equal to du. Okay, and from this relation we can write the relation of heat. Okay, now from this dq is just equal to du. Okay, why this is dq are equal to du, because from this one, okay, we know dv is 0, there is no change at constant volume, then we put dv is 0, then we get this term is 0, then dq is equal to dv. Okay, and in this relation dq is just equal, we put dq in place of du. Okay, now we get equation 2, and again we put constant pressure, then dq raise the temperature, and also volume are also increased. Okay, then this relation becomes, we write this relation, and our this relation is like this, right? And we write, in place of dq we write this one du. Now du is, we put the equation of this. Okay, in place of dq we put this relation, and in place of du we put this relation, right? And after equating this term we get this one. Okay, and for, we take the which case, we take for ideal gas. Okay, and we know for ideal gas pv is equal to mu rt. Okay, actually nrt na, here n is just equal to mu. Okay, we take the mu moles, that's why we write here mu. Now when we put mu rt, and we know the temperature is changed, that's why dt. Okay, and dv. Now we put the value of dp or dv, okay, from equation 4 to here. Now we get this one, and after calculating we get cp minus cv equal to r. That means cp is how much, what factors of cp is greater than cv, that's the r factors. Okay, that means if cp is 10, okay, 10 joule, then that means cp is greater than 10 joule, na? That means 10 joule plus r, that r factor is increased or greater, okay, to compare to our specific heat at constant volume. Okay, and this is called our Mayor's formula. Mayor's formula. Okay, so after that, thermodynamic state variable and equation of state. The thermodynamic state of variable is simply that variable which are required to specify the state of thermodynamics. Okay, and it may be intensive variable, that variable may be intensive or extensive. And intensive variable means that variable which are independent, okay, of the size of the system. Okay, if we take this or if we take this, here the variable are independent, there is not dependent their size. Okay, we take, if temperature 25 degrees celsius, here temperature 25 degrees celsius. Okay, their size is different but their temperature is same, right? That means this temperature is does not depend on the size of the system. So that variable is called what? Intensive variable. And similarly temperature is maybe pressure also, specific heat also a intensive variable. And that those variable which are dependent to the size of the system, okay, that are extensive variable. So you see the variable quantity which depend on the size, that is the volume. Okay, volume is, you see here the volume is greater. Okay, greater, and here volume is smaller. Okay, because that means volume are depend on the size of the system. Okay, and similarly entropy and energy, these all variables are depend on the size of the system. Okay, that's why there are extensive variable. And this all, pressure, volume, temperature, this all quantities are mathematically related, that are called equation of state. Okay, in thermodynamic system. Then thermodynamic process. So here some process are there. The first one is quasi-static process. This is the in this process the system, in which the system change its variable. Their variable is maybe pressure, volume, temperature. Okay, That means a process in which this variable is no show show a very small changes, okay, from its equilibrium. That means from their initial condition they doesn't have to show any large changes, okay. That process is quasi-static process. Okay, I repeat again, the system which show very small amount of changes in their variable. Okay, this means pressure, volume, temperature show a very small changes. That process is our quasi-static process. Isothermal process means, iso means same, thermal means temperature. Okay, so isothermal we take the temperature as a constant. Okay, that means there is no change in temperature, that is dt is equal to 0. Okay, that process is our isothermal process. And isobaric process, here we put pressure as a constant. Okay, and in that process internal energy, volume, temperature will be changed, okay, but the pressure will be kept as a constant. And isochoric, here we kept volume as a constant, okay, and we change the internal energy or temperature. Okay, then adiabatic process. Adiabatic is that process where there is no flow of heat. Okay, that means dq is 0. So we know that this is the system, okay, and this is our surrounding. Then adiabatic, when we call the process is adiabatic, that means there is no flow of energy. That means, sorry, heat. Okay, the heat does not flow outside, or the heat does not go inside, okay, from surrounding to system. So that process is our adiabatic process. Then cyclic process is that process where systems return to their initial state. Okay, if system have a temperature, suppose 10 degrees celsius, but due to some factor they are changed. Okay, and again after some time we get and we check the temperature is again we get 10 degree. That means their variable is returned to their initial state. Okay, that process is called cyclic process. And when there is no same, there is a difference. Okay, first 10 degrees celsius, then after some time it will be 8 degrees celsius. That means their initial, they doesn't equal to their initial state. That means these are the non-cyclic process. Okay, so my dear student, here I stop our class. Okay, in our next class we will discuss equation of ideal gas in isothermal process. When we put temperature as kept as a constant, then what will be the equation for ideal gas? Okay, so we will discuss in our next class. So my dear student, here I stop our class or video. Bye bye. So thank you for today. Have a good day. Take care. Bye bye.